using such a distribution, giving rise to various very strange kind of localization phenomena. But this is not physical. All right, this is something where you have an infinite diameter lens, and of course that's not a physical thing, and that's what's giving rise to things like this delta function in the power spectrum and this fact that there's no weight along the z direction. But it is a calculable limit you can take. So this is something, if you start reading literature, and after this lecture you want to learn more about this, you start reading papers about speckle and localization in speckle, which really care about this power spectrum. These are things which are somewhat wrong in the literature. All right, so various people have not been careful about this, and the real answer is that you have to go, there's no limit in which you can calculate the power spectrum and the intensity autocorrelation correctly for experiments, so you have to go measure it. And that should be really an input to theory. Here's, for example, a very careful measurement of the intensity autocorrelation in the power spectrum of speckle. And you can see it doesn't look like anything I've showed you so far. These are measurements by doing optical microscopy. It doesn't look like any of these theoretical distributions. But that's what it is, and the great thing about these experiments is that it's known, and really people should take these as input to theory. Okay, so it's just a caution that there's some problems in the literature. Yeah, go ahead.
What do you mean by the power spectrum?
The power spectrum, you could take the Fourier transform of the intensity autocorrelation, or it's power spectrum, right? Like a Fourier power spectrum. Any other questions? Yeah.
How far off is that from the equations you had before? Because while it's not exactly the same, it does look very close.
Yeah, but it's missing things like that horrible delta function, which is unphysical and gives rise to all kinds of things which can't happen.
Yeah.
And it has weight along the propagation direction of the laser beam, which is also really important because if it didn't, it would say particles could propagate along that direction without ever changing the momentum. Right? And that would confuse you if you tried to calculate what happened with localization. That has led to confusion in the theory literature, which is a little bit of a problem in my opinion. Okay. All right, anyway. So the last thing that Vadim alluded to is that, in fact, optical speckle is kind of truly bizarre. It has features which are not captured by any statistical measures, and no one really knows how much of a role that plays in localization phenomena in these experiments. So it's a really interesting theory question that's open. For example, Miles Padgett's group, who's done very careful optical microscopy in 3D of speckle, have shown that there are nodal lines. In optical physics, we call them optical vortices. Those these red things here, which are lines of zero intensity, which fully percolate in 3D, all right, and wander all over the place in 3D. There are also optical vortex rings which are present, which do something. Those are the teal things there. So, and in fact, there's other features present in the speckle which are not fully understood. So what impact this has on localization experiments, no one really knows. The optical vortex rings, we do know they probably don't do much because we know the intensity barrier around those rings is really tiny. But the fact that there are these sort of nodal lines, or these lines of zero intensity that fully wander in 3D, what that does, I don't know. All right, so there are good questions there to investigate. And that's why it's a topic of current research in optical physics, because it's really just kind of weird.
Is there any understanding why nodal lines exist? Like, is there any topological reason?
Yeah, you can think about it, right? So you have this random diffuser. There's going to be places where there's, just by luck, phases that wind around, right, which would give rise to these nodal lines and things like this. And people understand it. I don't understand all of it. Or maybe I used to, but I forgot. But there's papers by Miles Padgett's group and other groups. There's actually papers going back about 30 years. People have been studying optical speckle and trying to understand all the features of it. And part of the problem is it's just, you really need to do it in the lab because it's very difficult to propagate an electric field correctly in 3D. Yeah, go ahead. You had a question.
How exactly do they manage to get 3D measurement?
They do 3D microscopy. So you put a microscope on a thing and you translate it, right, with the optical speckle field, and you just do microscopy of it. Yep. And so that's kind of the neat thing about experiments using optical speckle or other kinds of optical disorder, which I'll talk about. You know it. It's constrained. You measure it. It's not something you don't know. Okay. Yeah, if anyone. Yeah.
So you get positive intensity is positive definitely. So if you find 1, 0 of intensity, it cannot terminate locally.
That's correct, yes.
Right? You're solving for a bosonic wave component, so you have to have lines.
Yeah, you do. That's true. Yeah. There's a lot of other features which exist too, which are not fully understood. Okay. So why did I tell you all this? I already kind of said all this, that there are lots of questions about how the properties of disorder affect localization that are not understood, and so there's a lot of great theory questions here to be answered and asked. Okay, so how do we use this in experiments? Let me start talking about experiments. That's optical speckle, that's how we get a potential out of it. People do lots of experiments with optical speckle. So Alan and the Space group, for example, has looked at localization in one dimension, and there's a reason I told you everything. So for example, they'll make a one-dimensional gas by taking a single red detuned focused laser beam, right, which is weakly trapping along the axis, and you can make a one-dimensional gas in that, kind of like a guide for the atoms, right? There's a reason I told you about that. So that's what they do. They trap atoms in a single focused laser beam, so it makes kind of a one-dimensional gas, and they superimpose speckle on that, coming down from another axis. Okay, and it makes a disordered potential for the atoms. Steve Rolson's group, a number of years ago, did experiments in 2D where they confined atoms to a plane using an optical lattice, or a couple planes. They confine atoms to a couple planes in optical lattice. So, if you make a vertical standing wave out of light like this, you get this optical lattice I showed you earlier. And if you're tricky, you can confine atoms to a plane or two. That makes a 2D gas, and then they focus, this is a picture doesn't turn out very well at all, but they focus the speckle beam down onto that plane to make a 2D disordered gas. Okay, so that's one thing people do. Now, I'll talk about the kind of localization or not that's been observed in these and other experiments tomorrow. One thing to keep in mind about speckle in 1D and 2D that has been bothering people and caused some trouble for a while is that classically traps the atoms. So if you take a slice, let's say, of 2D of the speckle, there are potential minima that are present, and those potential minima will trap atoms classically. They'll just get trapped in there. And that threshold for trapping is known, average over all disorder realizations. It's about half of the average disorder energy. A particle with less than that energy will get trapped. That happens in 1D and in 2D. And in 1D, this led to some confusion over initial results of localization. Okay, so in 3D, this doesn't happen because the atoms can always wander away. There's no local minima. There's just saddle points in the intensity in 3D. And there's a whole papers written on the saddle points and intensity in 3D speckle. Okay, so in 3D, people also do experiments. My group did an experiment where we just have a single speckle beam that's extending in 3D and released a gas into it, and we're able to see Anderson localization that way. And first the Space group and then Nguccio's group also did experiments where they took two speckle beams and crossed them to make 3D disorder. And they ended up with 3D disorder, 3D speckle, but also with additional interference between those laser beams. They had the same intensity. So you can see some of those interference planes here in the speckle. All right, and they're showing the intensity autocorrelation, and those interference planes show up in that as well. You can kind of barely make out some stripes there. Okay, so that's kind of what I would say are bulk gases where people apply disorder in 1D, 2D, 3D, and watch what happens. And tomorrow I'll talk about what happens and what's been observed. One thing I want to talk about too is experiments my group does and other groups where speckles combined with optical lattices to realize disordered Hubbard models. And also to look at things like Anderson localization for non-interacting gases in models like the model Vadim wrote down. Okay, so how does that work? So this will be specialized to my group somewhat, and then I'll go back and come back to other groups after a small digression here. So let me just mention a little bit more about how an optical lattice works, because I think this is kind of important. This is how people make things like Anderson models or Hubbard models. My group and other groups have done this. So let me just first tell you how the non-disordered case works, and then I'll tell you what it looks like when disorder through optical speckles added to this, or using what are called incommensurate lattices, which make a kind of pseudo-disorder. All right, so here's an optical lattice. I talked to you about this in the first lecture. If you take two laser beams with the same polarization and shoot them at each other, you get a standing wave. The spacing is half the wavelength, so about 400 nanometers to 500 nanometers in most experiments. You will hear AMO people use recoil energies as a unit of energy. So we measure the potential depth here in units of those recoil energies, which is just h squared over 8md squared. For rubidium-87, which is one atom my group works with, and a typical lattice people would use, it's about 170 nanokelvin, which is a characteristic temperature scale I told you earlier.
Typically, what is the order of trapping?
What, I'm sorry, what's that?
So the trapping can itself localize the atoms.
Yeah, so there's also always, and I'll come back to that, there's always a trap present in these experiments. So, almost. So, for example, in some of these experiments, like this experiment and this experiment, there's trapping in 1 or 2 dimensions present. In some of these experiments I'll talk about tomorrow, like this experiment by Spey, the trap is released in one direction to allow the gas to expand and try to see how diffusion works. In other experiments like this 3D experiment and this 3D experiment, again, you're letting the atoms go. In the experiments I'll talk about right now, there's always a trap present. I'll talk about how that comes in and how that changes some of the physics of the optical lattice as well. But there's always in these experiments here I'm talking about, there's always an overall trapping potential present.
So if you're letting it go as a time of flight type measurement,
Yeah.
then
You turn everything off. You turn the trap off, you turn the lattice off, everything.
so then that trapping physics is not relevant to localization.
Well, no, the trapping physics is definitely relevant. Oh, so people, to back up a step, people have observed localization in a couple different ways. One, and I'll talk about this in detail tomorrow, one is through diffusion, by turning the trap off, keeping the disorder there, or a 2D or a 1D trap there, and let the atoms go. That's one way. Then the trap is now playing a role in the localization. People have also done measurements, which I'll talk about tomorrow, that involve conductivity, coherence, and excitation spectra to try to see localization that way, and that's with the trap present. And the trap may be doing something in terms of localization physics there. Okay? So I'll get into all that tomorrow when I talk about localization phenomena. This is more just kind of like a methods talk. What's the stuff behind all of it? Okay, does that make sense? Yep, good. Any other questions? These are great questions. Okay, so in these optical lattices, particles can do two things. They can tunnel from site to site, which gives rise to this tight binding model that Vania wrote down. And if two particles are on the same site, they interact with this low energy collision I talked about. So the atoms in these optical lattices, if they're fermions or bosons, they can realize what's called a Hubbard model, which probably everybody here is familiar with, where there's a tunneling term, an interaction term. If the atoms are fermions, so like potassium-40 or lithium-6, then the interactions are only between atoms in different states of spin. If they're bosons, atoms with the same state of spin can interact. All right? Yeah?
What is S?
Yeah, so S, so we measure, okay, so to back up a step, the potential depth here can be controlled by the intensity of the laser beams. So it's tunable, right? Big to small. That's how actually T is controlled and U is controlled, all right, by tuning this. If I make this very big by making the laser beams very powerful, then T gets very small because the potential barriers are large to tunneling. U actually grows a little bit because the atoms are squeezed together a little bit more, and that mean field energy shift grows. Okay? So S here, okay, so people use all different kinds of nomenclature. Here, the basic unit of this potential is a recoil energy, and S is how many recoil energies I've got, which I just tune up from 0 to 1 to 2 to 3 to 4 to 40 by changing the power in the laser beams. Yeah?
So can you tune T and U independently?
Yes. How would you do that?
How would you do that?
That was good. Well, U I can tune independently using a Feshbach resonance.
Okay. Right.
All right? Because I can tune the scattering length, and U is proportional to the scattering length. I'll mention that in a bit, but that's kind of obvious.
Yeah.
Yeah. Yeah. And people do that. With atoms that have Feshbach resonances. Not all atoms have them, or good ones, or ones that are convenient, or things like this. It depends on the detailed shape of that potential and where the bound states lie. Okay. I had in here a bunch of stuff about band structure, which I think is maybe kind of silly with this audience. You know, let me back up a bit here. There is, in this lattice, what do I want to look for here? there is a band structure, all right? So just like particles in a solid have a band structure, there's a band structure here. Here's a plot of the band structure for a 1D lattice. There's a band gap, and the tunneling energy sets a band width. And most of the experiments are done with atoms just in that ground band, the lowest energy band. So they're cooled to low enough temperature, so just in that ground band. And the atoms down there have a dispersion, which is cut off, which is 2t 1 minus cos pi q over qb, where qb is the edge of the Brion zone. Okay? So there's a band structure. Everybody's familiar with this? I probably don't need to draw it. Okay. So one thing I do need to do here is talk about the fact that, in a band, in a system with band structure, the eigenstates are Bloch waves, right, which are delocalized over the whole lattice and can have a well-defined quasi-momentum or crystal momentum. We also sometimes work with Vania orbitals, which are localized states formed out of superpositions of Bloch waves. And those Vania orbitals are convenient because they allow us to calculate, to make this Hubbard model by discretizing the model in terms of lattice sites and expanding field operators in terms of those Vania orbitals. Those Vania orbitals are not eigenstates. Of course, if I put an atom there in a clean lattice, it will just tunnel away, right? Because the eigenstates are Bloch waves, which are delocalized. All right, so in the interest of time, so using those Vania orbitals, it's relatively easy. So you've got the band structure, which you can calculate for a cubic lattice. I can even do it, it's not hard. You can, if you think in terms of Vania orbitals, and you can calculate the Vania orbitals here because, very simple lattice, sinusoidal lattice. You can also calculate the interaction energy, and in a Meade field sense, the interaction energy is really just the formula I wrote down previously, but now the wave functions are the Vania orbitals for that site. And so you just have an integral over the wave function of the fourth power, and it's proportional to scattering length. So you can tune that interaction either by tuning the lattice depth, which makes the Vania orbital smaller and increases the peak value of the amplitude, which makes this bigger, or you can tune this independently by tuning A using a Feshbach resonance. Okay, so those are where the two elements of the Hubbard model come from. There's tunneling, just like in any lattice system, and then there's a band structure, and then there's interactions from that low energy collision, and we calculate this in that contact potential, which I mentioned previously. Okay, so is that, I don't want to, probably the day is getting late, and that's good enough. All right. So that's how we get all the pieces of this Hubbard model, how we adjust it. Okay, any questions about that? Okay, let me mention something very important, which is also a point which is not completely explored in experiments. So, in fact, you have this lattice potential here. Sorry, it's very hard to see. This projector, you have this lattice potential, but there's always this trap which is present. Okay, and tomorrow I'll be a little bit more explicit about writing down Hamiltonians with the trap. I didn't write this down here, but there should be a trapping term. Okay? But here it is in a picture. So in fact, the exact eigenstates, single particle eigenstates of this potential, where you have a trapping potential and a lattice, are known. And here are those eigenenergies versus quantum number. All right, so there's a remnant of the band structure here. That's this, and here's 4t on this plot. But there are these funny states that come in that are doubly degenerate, which don't look anything like the band structure. And you'll notice there's no band gap anymore. So what are these states? Actually, I can plot these states for you because I can calculate them. Sorry, cut off on the bottom again. So this lowest energy state, what it is it looks like a harmonic oscillator state modulated by the lattice. You could have guessed that or drawn that by hand. N equals 5, to go back, that's a state which sort of looks like a band structure state in here somewhere. It looks like a harmonic oscillator state modulated by the lattice, right? Somehow we should, undergraduate physics would tell us this is what it has to be. These states, which are out here, which are doubly degenerate, these aren't like any states from either example, from the band structure or from the harmonic oscillator potential. These are single particle localized states that exist out on the edge of the trap. They're localized out there. They're doubly degenerate because we can adjust parity between these things. So there can be ones with opposite parity out here. And those are states which don't exist in normal band structure, don't exist in the trap on their own. And kind of what they are is they're states which have a turning point out here somewhere, and then are Bragg reflected as the particle hits that turning point, comes back around, and Bragg reflected out here somewhere. So these states are known. They're first understood by Marcus Riegel and later written down analytically by Anna Maria Ray. And what these states mean is that, the system is not really gapped. And so some of the things you read in papers are also a fiction.